Assalamu alaikum wa rahmatullahi wa barakatuh. So today we are going to continue. This is week 14. Next week will be the last week. Okay. So I hope you have started preparing for the final. And today, you need to come to the lab for your term project. Okay. So all of you should be there, both groups 1 and 2, and then we'll discuss about the assessment criteria. Okay. And try to reach some common ground. So on the design of single pipelines, we design single pipeline without a pump. Now, what happens when you have a pump? You see, in the previous one, yeah, oh, okay. Yeah, without a pump. Yeah, without a pump. So we only took care of the head loss due to friction, okay? Because the pump head and the turbine head is 0. Now, all we need to do is to introduce the pump head in the energy equation. That's just it. Because pump head adds energy to the flowing fluid. So we have to add plus HP to the pump head. If we have a turbine which extracts energy from the system, we have to add the turbine head here plus HT, turbine head. Okay? So when we have a pump, we will just add the pump head and then solve the problem in a similar way as this one. Okay? So now, design of single pipelines with pumps. In waterworks and wastewater systems, pumps are common at the source to lift the water level and at intermediate points to boost the pressure. For waterworks, for instance, you need pumps to lift water level, okay, from the intake to the treatment plant, okay, and from the treatment plant, you need pump to high lift pump to the distribution system or to the storage facility, okay? And at intermediate points within the water distribution network, you have to boost the pressure because as the water is flowing, it is losing pressure. The pressure is reducing due to the head loss, okay? Due to the frictional head loss. So at some intermediate points, you need to install pumps to boost the pressure, okay? And the same thing happens with wastewater systems. Okay, normally sometimes you need pump, to pump it, for instance, in case you need to pump it against gravity. Okay, and figure 15.8 illustrates a situation where water is supplied from a reservoir to an upper level reservoir. Okay, so this is the figure from a reservoir to an upper level reservoir. So you can view this as if you have, let's say, water source, which can be a river or a dam, okay, a reservoir created, okay, a reservoir created, okay. So and then you need pump to pump it to the treatment plant, okay. So in this case, you can see there will be entrance loss through the pipeline, okay. You can see the energy grade line dropping immediately it enters because of here, okay. And the hydraulic grade line moving constantly, the difference because of the constant velocity, okay. And then at this point, the energy grade line is boosted up by the pump, okay. You can see it shoot up, okay. And then it moves steadily into the other reservoir, the energy grade line and the hydraulic grade line, okay. So this is the pumped head, okay, which is HT, okay, pumped head, okay, which we have to add in the energy equation, okay. We have to add it to the energy equation. And how do we do that? To analyze the system, all we need to do, you can see it now, HP, which is the energy equation here. the pumped head added. And then if we have any minor losses, the frictional head loss, like I say, is the major loss. Normally, we just use it as head loss, which is equal to HF, the frictional head loss, plus HM, minor losses. Okay, so if you want to include the minor losses, we just add it to the frictional head loss. And I explained the source of the minor losses, at the entrance, at exit, and at bends and all that. You will all have minor losses. Okay, so here, when you make the pump head the subject of the formula, you can see this, because this is the piezometric head, okay, and the pressure head. The pressure is atmospheric, so P1 equal P2, which is 0, because it's atmospheric, which is 0 gauge. Okay, so, and then you have here Z2 minus Z1, which is delta Z, and then the head loss, because these two is equal to HL. Okay, so the pump head will take care of the difference in elevation and the head loss in the pipeline. Okay, and the head loss in the pipeline. If you remember, we even saw something similar in fluid mechanics, okay, where we apply the pump head. Okay, so HP is the energy added by the pump, okay, and delta Z is the difference between piezometric heads or water levels after pumping and before pumping, okay, and HF, the frictional head loss, determined usually using the Darcy-Weisbach equation or Hazen-Williams, and you have the minor losses, the general form of which is given by this, okay, and then the energy head, which is the pump head, is now converted to power, okay, brake horsepower of the pump using this formula, okay, which is the brake horsepower, gamma Q HP over the efficiency, okay, over the efficiency. So this is the overall pump efficiency eta, okay. Even this formula, we used it also in fluid mechanics, okay, so it is similar to what we have. So let's take an example and apply it. Here you have water has to be transported at a rate of 1 cubic feet per second from a reservoir of water elevation 1000. Okay. Okay. So let's try to, water has to be pumped at this rate from a reservoir of water elevation 1000 to a reservoir of elevation 1010 feet through a 4,000 feet long 6-inch diameter steel pipeline at 50 degrees Fahrenheit. Okay. Determine the horsepower of the pump required, having an efficiency of 70%. Disregard the minor losses. Okay. So this is like similar to this one. This figure, it has to be pumped from lower reservoir to higher reservoir. Here 1000, here 1010. So the difference in elevation 100 feet, 100 feet, which is 30 meters. Okay. So, and we want to find the horsepower of the pump. Okay. So the difference in elevation delta Z is 100 feet. Okay. We are to disregard minor losses. Okay. So HM equals 0. Okay. But major losses, in this case, we cannot disregard them. The pipe is long. Okay. You remember when the pipe is long, major losses, the frictional head loss plays significant role in that case. So what's the velocity of flow? We have the flow and the area we can find by pi d squared over 4. Okay, so this is the velocity of flow and the Reynolds number, Vd over mole. Okay, this is it. And then the relative roughness, we have to go to that table and get the epsilon, the roughness for what is the pipe type? Steel pipeline. Okay, so which is 0.0015. Okay, and the diameter is 0.5. Okay, and then this is and then we go to more Moody's diagram. Okay, Moody's diagram. At this Reynolds number, I have taught you how to use the Moody's diagram in the previous lecture. Okay, so you use this Reynolds number 1.81 exponential 5 and this relative roughness 0.0003 and obtain the friction factor 0, which is 0.0265. And then we use the Darcy-Weisbach formula where we put the friction factor F here. Okay, and then the other parameters, this is L over D, this is V, okay, this is G, okay, to get the frictional head loss. And then from there, we can simply insert it here because the frictional head loss is the head loss because minor losses are 0, okay. So this is the pump head. So the head of the pump, it has to provide this head 185.6 to overcome the elevation difference and the frictional head loss, okay. And then what is now the power of the pump horsepower, okay, which is gamma Q HP over 550 eta for imperial unit, okay. Gamma is already known, so we already found HP, okay, and this is rho G for water, okay. Eta has already been provided from the problem, so the pump is 30 horsepower, which has so much, you know, it's a big one. It is a high capacity pump. You can imagine the pump to, let's say, lift water, let's say to a one-story building, you may need maybe 1 or 1.5 horsepower, okay. So this is 30 horsepower, and that's because of the elevation difference, you know, 30 meters. So it is really, the height is much, okay. Let me check. So you, some of you are typing. Let me see what you are typing. I'm done. Until design pump, I think they have to focus on point of pressure. My question about design pump, what the points that it has to focus on? Yeah, we have to focus on to evaluate, like I was explaining. Let me go back to the slide to explain what do we focus on. We focus on the pump head. Okay, we focus on the pump head. And how do we determine the pump head? We determine the pump head using the energy equation. And based on the pump head, we now determine the pump capacity. Okay, the pump capacity. Because when you go to the market, you want to buy a pump, you don't go and tell them, please give me a pump that will lift water from over an elevation of 30 meters. No, you give them the capacity. Okay, I need 1 horsepower pump, 2 horsepower, 5, 10, 20, 30. Okay, so you need to do your homework. Okay, like in this case, the pump capacity based on the efficiency, okay, is 30 horsepower. So you just go to the market and tell them I need 30 horsepower pump. And when you install it, that pump will be able to lift water, you know, through an elevation difference of 30 meters. Okay. Now, pipes in series, okay? Pipes in series or a compound pipeline consists of several pipes of different sizes connected together, as shown in this figure. If you see this, you know, D1 is different from D2, it's less than D2, D2 is, sorry, D1 is greater than D2, and D2 is less than D3, okay? Then you have Q1, Q2, Q3, HF1, HF2, HF3. Okay. Now, according to the continuity equation, that is, you know, the mass balance equation. Okay, because it's from the mass balance that we get the continuity equation. If you remember, you know, even in fluid mechanics. So the energy equation, the following terms apply to the pipelines, because the rate of change of mass within the system is 0. Okay, there is no accumulation. So in is equal to out. Okay, mass in is equal to mass out. Okay, so rate of mass out of the system minus into the system is equal to the rate of change of mass in the control system. Okay, so this is 0 because there is no accumulation. So in this case, rate of mass into the system or out of the system is equal to rate of mass into the system. Okay, and what is this rate? is simply rho QA. Okay, it's simply rho Q. Okay, this is the rate of mass inflow. Okay, which is rho 2 Q2. So density remains the same. So that means Q1 equals Q2. Okay, so Q1 equals Q2, so it is constant equals Q3 as well. Okay, so that means the flow rate is constant throughout. Okay, if the flow rate is constant, now what happens to the frictional head loss? The frictional head loss is the sum of the head loss in the system. Okay, so the total head loss in the combined system is the sum of the individual head losses in the individual pipes, because they are different, because they have different length, different diameter, and what have you. So definitely the head loss in each of the pipes is going to be different, and the effective head loss, the net head loss in the pipeline, for the series is going to be the sum of the individual head losses for each of the pipes. Okay, so for analysis purpose, the different size pipes are replaced by a single pipe of a uniform diameter of a length that will pass a discharge Q with a total head loss HF. Okay, so once you find the total head loss, Q is the same. Okay, so this system can be replaced with a uniform pipeline of uniform diameter and length. Okay, so this is known as the equivalent pipe. Okay, now this is pipes in series. The bottom line here is simple. For pipes in series, the flow rate is the same throughout because of the continuity equation, while the head loss is the sum total. The net head loss in the system is the sum total of the individual head losses within each of the pipelines. Okay. What about if they are to be in parallel? What is going to change? For compound pipe system connecting two reservoirs, you can have like 6-inch diameter here, 3-inch here, and 4-inch here. Okay, with the energy, there will be entrance loss here. Okay, the energy grade line, the energy line going down at the entrance. Okay, as you can see, because of the entrance loss. Okay, so this accounts for the entrance loss. And the hydraulic grade line. Okay, here, because of the change in diameter, V1 here, V2, V3. Here, V2 is greater than V1 because of the reduction in the cross-sectional area. Okay, so V2 is greater. So once the velocity is greater, you realize that the velocity head increases when you have increase in the velocity within the pipeline. Okay, and this is a fact when drawing the energy line, grade line, and the hydraulic grade line. When the velocity increases, the velocity head increases as well because it is a function of velocity. Okay, and then when it reaches pipe 3, V2 is less than V3 is less than V2. Okay, because of the increase. V3 is V2. So sorry, this is greater than this. Okay, and no, this is greater. V2 is greater than V3. Yeah, V2 is greater than V3. So V3 is less, and that is why you can see here the velocity head reduces as well. When you look at this figure, this is 6-inch diameter, 3-inch, 4-inch. Between V1, V2, and V3, which one is greatest? Who can tell me? Which one is greatest? Which one do you have the maximum velocity here? Just talk, I have enabled your mic. And why? Yeah, can you talk?
V2.
Which one? Okay. So now I want to say between V1 and V3, which one has greater velocity between V1 and V3? Where do you have velocity? Which one
I
has
think
greater
V3.
velocity? V3. Why? Why is that?
Because the water in the pipe is accelerate, and the V3 has the maximum velocity
What? Because V3 has what?
because the water in the pipe is accelerate.
Yeah, but what term do you use to judge that? I mean, it can be accelerating uniformly. It can be accelerating. It can have uniform acceleration. Look at the diameter from Q equal AV, which is constant. Okay, the area, this is what, pi d squared over 4, and the velocity, which is constant. So now it means when the diameter decreases, the velocity will increase, isn't it? Pipe 3, the diameter is 4-inch. Pipe 1, the diameter is 6-inch. So it has smaller diameter than pipe 1. In that case, the velocity will be higher. Hence, V3 will be greater than V1, isn't it? Do you understand?
Yes.
Okay. So now, in this case, of course, so that means in actual sense, when drawing this, the velocity head should be greater here than here, isn't it? The velocity head here should be greater in the third pipe than in the first pipe, okay? And then here you have entrance loss. Here you have enlargement contraction loss. Here you have enlargement loss. You have exit loss. You have entrance loss. All these are the minor losses, okay? All these are the minor losses, which are way smaller than the frictional head loss in the pipeline, okay? Which are smaller than the frictional head loss in the pipeline, okay? Now design of single pumps with single pipelines with pumps. No, I have already explained this. Now, parallel. Okay. Now we move to parallel pipeline. Let me see. Did I repeat? Okay, from here. Okay. So I think I repeated this. Okay, I repeated this slide. All right. Okay. Now for parallel. So if it is in parallel, for the parallel or looping pipes, okay, we call it looping pipes, okay, in this figure, okay, the continuity and energy equations provide the following equations, okay. The inlet flow Q is distributed into Q1, Q2, Q3, okay, but the outlet Q is the same because of continuity, okay. So Q is the sum of the flow rates in this, in that, in this, okay? But because they will add up to become the same Q that came in, okay? So Q is equal to Q, okay? And Q is the sum of the flow rates in the pipeline in each of the branches, okay? And then what about the head loss? The head loss is constant in this case. More often than not, you realize that they have the same diameter, okay, the same diameter and even length, okay. So in that case, that will make the head loss to be the same, okay. And if you remember, the frictional head loss is L over D squared over 2G. So if L and D are the same for the pipeline, then basically, by and large, they will have the same frictional head loss. Okay, so the head loss is the same in the system. Okay, HF is equal to HF1 is equal to HF2 is equal to HF3. Okay, So the system will have the same head loss, okay, which is HF, in which you can use any of the head loss for any of the pipes, okay? But the flow rate is the sum of the flow rates in the system, okay? Flow rate is sum of the flow rates in the system. Now, here we have started with single pipeline, parallel, in series pipeline, and then loop. Now we will move to another topic called pipe network analysis. We are gradually moving into the water distribution system design, okay? We are gradually moving into that. We started with the design of a single pipeline, isn't it? Now we will gradually move into like design when you have multiple pipelines, okay? Let's say for a town, okay? So we will move into that, and this will come under the pipe network analysis or pipe network design or water distribution system design. So an extension of pipes in parallel is a system in which the pipes are interconnected to form a complex loop configuration. Okay, the flow to an outlet comes from several paths. Okay, the flow to an outlet comes from several paths, and analytical solution of such system referred to as pipe networks is quite complicated because you have several pipes connected together. So the analytical solution is quite complicated. But there are three simple methods to be used. We have the Hydrocross method. Hydrocross is a professor of civil engineering in the States who developed the method, which is also called the head balance or loop method. Okay, we have other methods of analysis called the linear theory method, LTM, and the Newton-Raphson method, which utilizes the Newton-Raphson iterative procedure. Okay, but for the sake of the water engineering, we will look at the first method only, the Hydrocross method. Okay, of this, the Hydrocross method, which involves a series of successive approximations, it's an iterative procedure, meaning you keep on correcting, coming back, first iteration, second iteration, until the change in the delta Q is very small. Okay, so it involves a successive approximation and corrections to flows in individual pipes, and is a popular procedure of analysis. And between a loop and a branch pipe network, which one is better? Between a loop and a branch pipe network, we explain, like the loop network is like the grid, okay? Like the grid, where it can have water from different points coming, and the branch network, is branching, branching. So which one is better? We already explained before, if you remember, the branch network usually for smaller towns, okay? But there are dead ends, okay? Like if maintenance is being carried out here and you short the valve, at this point, water will not reach this node, okay? So it has many dead ends. While for the grid system, each node receives water from more than one point. So if you short one of the points, the node can receive water from another point, okay? But you can see the grid system has more pipes, so it is more expensive than the branch system, okay? The branch pipe network, okay? So here, most of the major times, usually a distribution network has a combination of the two. Some portion can be supplied using the grid system and others using the branch system, or it can start with a branch and then end up with a grid system. Okay, and then we are going to analyze, the Hydrocross method which we will take is a procedure for analysis of the grid system or the loop system. Okay, closed loop. Okay. Now, what is the Hydrocross method? What is it based upon? Okay, it is based on upon the fact that the sum of head losses around any closed loop is zero. Okay, that is summation HF equals zero. Okay, the sum of all head losses around any closed loop is zero. So here, when you this is upon the fact that you look at the flow rates, okay, the flows in the pipes, and try to give them direction. So sum of flows within a loop, okay, the sum of flow rate, okay, that is algebraic sum, okay. You have positive and negative. Clockwise, you assign direction. Clockwise flows to be, let's say, positive, and counterclockwise to be negative. So the total sum of the flow rate should add up to be 0. And if this add up to be 0, then the head loss, which is, summation k q squared, if q summation q is 0, so this is k summation q squared, which is 0. So it will also give you 0. Okay. So that is why we have the sum of the head loss to be 0. Okay. And if we consider that QA is an assumed pipe discharge that varies from pipe to pipe of a loop to satisfy the continuity flow, okay, to satisfy the continuity flow for each junction, meaning inflow must be equal to outflow. Then del is the correction made in the assumed flow, because this is assumed. Okay, so this is the correction made in the assumed flow of all pipes. Okay, and then by substituting in the general head loss equation, which is summation k q squared, okay, or q to the power of n, okay, is q squared if we are using the Darcy-Weisbach equation, and for Hazen-Williams equation is 1.85. Okay, but the general form is kq to the power of n. So the summation is summation k, and this is the the constant. Okay, it's a constant. Now we can now correct it, qa plus delta n, delta to the power of n equals 0, and we can use the binomial equation to expand this. When we expand, you realize that delta is given by summation kq to the power of n over n times summation k q to the power of n minus 1. This is n minus 1. Okay, this is n minus 1. Okay, which you can simplify. It to be, because this is simply summation hf. Okay, and this is simply, summation k qa to the power of n over qa. Okay, so this is summation hf, this is hf, and this is over qa. Okay, so now del, which is the correction to the assumed flow in the pipe, is given by summation of the head loss over n into the summation algebraic. This is algebraic, sorry, the absolute. Okay, absolute sum of the head loss over f. Okay, absolute sum of the head loss over f. Okay, so here equations 15.17 for Q and 15.29, which is this one for delta, are used in the Hydrocross procedure. Okay, and the values of n and k are based on the Darcy-Weisbach or Hazen-Williams equations. Okay, they are based on Darcy-Weisbach or Hazen-Williams equation, which is obtained from table 15.2. okay, which is the value of the constant here, k. Okay, we know for imperial unit is different for the other one, Hazen-Williams, sorry, for the SI unit is also different. Okay, we already introduced all these tables before. If you look at them, let me briefly take us back to the table so that you just, yeah, K, equivalent resistance K. Okay, this is for the Hazen-Williams and Darcy-Weisbach. So K here for SI unit is equal to this. And in the previous lecture, I have shown you how K is equal to this using the Darcy-Weisbach equation. Okay, it's simply using the Darcy-Weisbach formula, HF equal, F L over D squared over 2G, where you substitute V as Q over A, and A for pipeline is pi D squared over 4. So when you simplify this, you realize that you have just KQ squared, okay? And the coefficient K will be equal to the constants, F, L, D, and other stuff. This I derived in the previous lecture. So now, what are the procedures for the Hydrocross method? Okay, you divide the network into a number of closed loops. Okay, and the computations are made for one loop at a time. Okay, one loop at a time. You compute K for each pipe using the appropriate expression in the table I have just shown, and then you assume a discharge QA and its direction in each pipe of the loop. Okay, and at each joint, which is a node, the total flow in should be equal to the total flow out. Q in equals Q out, according to continuity equation. And you should consider the clockwise flow to be positive and counterclockwise to be negative. These are just conventions. You may choose to take another way, okay? Okay, but here we'll be assuming clockwise flow to be positive and counterclockwise to be negative. Let's assume we have this loop made up of 4 pipes, okay? So clockwise flow to be positive. So if we assume the flow in this pipe is this direction, this one is that direction, this one is this direction, this one is this direction. So the flow here, the flow in this pipe is against the clockwise, okay? It's counterclockwise, okay? So it is negative. Here is also, no, then let me give this here. This one also, let me make, so this is clockwise, and this is counterclockwise. So they will be negative, okay? So you assume the flow rate inside based on the initial flow, because there must be initial flow into the network, okay? So based on the initial flow, you divide at each junction. We will use an example and demonstrate this application, okay? And then you compute the head loss, HF, in column 5 for each pipe, retaining the sign, okay, of column 4, and the algebraic sum, which is summation HF, okay? So you will compute the head loss based on the flow rate. If it is positive or negative, you maintain it also for the head loss, okay? Because this is the algebraic sum of the head losses. And then you compute HF over Q. In this case, this without regard to the sign, because we use the absolute value here, okay? And then you determine del using the equation, okay, and apply the correction algebraically, apply the correction algebraically to the discharge of each member of the loop, okay? And then for common pipes, because if you have another loop here, you can see this pipe is common between loop 1 and loop 2. Okay, so for common pipes, we call it common pipe. For common members among the two loops, both del corrections should be made, one for each loop. Okay, so you correct it twice. You have two ways. Either you correct it before you move to the next loop, or you get the value of the correct del for the second loop, and then apply del 1 plus del 2 and correct it for the common pipe. Like I said, we will take an example to demonstrate the application of the Hydrocross method, okay? And then you, for the corrected Q, you repeat steps 4 through 7 is repeated until del becomes very small for all the loops, okay? So that depends on the assumed flow rate, okay? Let's take an example to demonstrate that. And then once we do that, if we're able to, if we take it, then we can now await, for the next lecture, which is next week, where we will do the pipe network distribution design. Okay, this is part of the design analysis. Pipe network analysis is the preliminary aspect of the design. So make sure you understand this pipe network analysis very well. You can see it may be somehow cumbersome because normally we use computer to do it, and it takes time. There are, in fact, some of them that you cannot do it manually. You cannot do it manually depending on the number of loops. Okay, you cannot analyze it manually. So we use computer programs. We develop programs, both in course. In fact, during my undergrad senior design project, I developed also a program for the analysis of network in Fortran using the Hydrocross method. Okay, and you have other ready package, software for the analysis like EPANET, like WaterCard. Okay, because there are things that are central to the design of any water distribution system. Okay, so let's take a few minutes break, and when we come back, we will now look at the practical example of the Hydrocross method, where we will determine all the pipe diameters, all the parameters needed. Okay. All right, guys, we're back. Let's see. One person is absent today. Who is that? Amjad, no connection. But Amjad was here. Ahmad, Hamdan, Khalid. Where is Amjad? He was here. I think I had his voice. Okay. So let me go back and make it in the presentation mode. Okay, so here it says find the discharge in each pipe of the welded steel network shown in figure 15.14. The pressure head at A is 100 feet. The pressure head at A is 100 feet. Where is the network? This is the network. We are given this is the total inflow into the system, into the distribution network. 4.35 cubic feet per second is our total Q, okay, into the system. This Q can be the supply from a storage reservoir or direct pumping from a water distribution plant, okay. And we are given the pressure head at A, okay, node A, okay, to be 100 feet, which is the piezometric head, okay, or the hydraulic head, okay, at A. And what do? We are given also the length and the diameters of the pipes. So this is the length in feet, and in inch you have the diameter of the pipe, okay, for each case. Length, diameter, length, diameter, length, diameter, okay. And then from the problem, we are also given all the nodal discharge, nodal outflow from the node. This is B, D, E, C. Okay, these are the nodal outflows. From continuity, if you look at the nodal outflows, when you sum them up all together, they should give you 4.37. That is when you sum up 0.35 plus 0.42 plus 3.11 plus 0.49. They will all add up to give you the total inflow, which is 4.35. Okay. These outflows at the nodes are abstraction. Because here you have different houses, okay? Houses are all scattered around the nodes, okay? So this outflow is supplying some buildings in this area, okay? The same thing here, okay? They're all supplying buildings, houses, maybe even some industries, if there are industrial areas around them, okay? Although, like we mentioned, for small industries, yes, but for large industries, they normally have their water supply system. Okay, they normally have their, water supply different from the municipal water supply because of the huge amount of water that they utilize in the industrial operations. Okay, so the first thing we do based on the procedures, we divide the network into a number of loops, and the computations are made for one loop at a time. So here we have only 2 loops, isn't it? So we number it loop 1, loop 2, okay? And then we now compute K, okay? We now compute K, okay? Compute, which is step number 2. Compute K, which is the resistance coefficient for each pipe using the appropriate expression, okay? But to compute K, you will need to if you look at the table, which I have shown you, which you have, you can compute K simply if you are using the Hazen-Williams, because here is the Hazen-Williams, and we are using the imperial formula, okay, in which you have Q in cubic feet, length in feet, diameter, the diameter in feet, although we convert it to inch, is given in inch, so we can convert it to feet, and the head loss will be in feet. Okay, so here the head loss is given if you go to table 15.4. So the head loss is given as simply 4.73 L divided by C, which is the coefficient of the Hazen-Williams equation, to the power of 1.85. And then D, which is the diameter, to the power of 4.87. Okay, so this is how K is computed for each pipe, meaning we can compute K without knowing the flow rate. Okay, all we need is the here normally we for the pipe, the constant, Hazen-Williams constant for the pipe is assumed to be 120 for each of them. Okay, so we only change the diameter and the length. Okay, and then we get the K for A, B, A, C, all the pipes. We have a total of 6. Okay, so this is the coefficient, the equivalent resistance for each of the pipes. What about if we are to use the Deci-Weisbach equation? If we are to use the Deci-Weisbach equation for the imperial system, we use FL based on the table over 39.70 D to power of 5. Okay, so here we have L and D. So to get F, the friction factor, if it is provided to simplify the matter, fine. If it is not, you can get the friction factor by computing the Reynolds number and the roughness, E over D. Okay, E over D. Okay, and then when you do this, you go to the Moody's diagram based on the Reynolds number and the relative roughness to get the friction factor. This we have done in the previous examples, okay? Or if the friction factor is provided, fine, okay? You only need the length and the diameter, which you can substitute to get the equivalent roughness using the Deci-Weisbach equation. So this is using the Hazen-Williams equation, okay? So once you compute the relative roughness for each pipe, we now go to step 3. Okay, and step 3 is saying that you should assume a discharge QA and its direction in each pipe. This is just arbitrary, okay, but you should also bear in mind that the total discharge, at the should be equal to 0, meaning inflow should be equal to outflow. So total discharge equals 0. Okay, meaning inflow should be equal to outflow. So this is just the guiding principle, okay? So here at each joint or node, the total in should be equal to the total flow. The total flow in should be equal to the total flow out based on continuity equation. And we will take clockwise to flow to be positive and counterclockwise to be negative. Okay, so you see the inflow here at point A is 4.37. So we now divide it, okay, arbitrarily, okay? So if you go to this table, A, this is where we divided, we assume the discharges, okay? And it's arbitrary, okay? Like I said, the only guiding principle is inflow is equal to outflow. Here, 4.37. So we assume 2 will go this way in this direction, and 2.37 will go in that direction. Okay, 2 plus 2.37 is equal to 4.37. That's the most important thing. At every junction, the sum of all the flow rates must be equal to 0, or inflow must be equal to outflow. Simple. And this is the continuity equation. Okay, so now when 2 cubic feet per second comes to joint B, what happens? 0.35 is already provided from the question. Okay, so It means out of these two, 0.35. Let me get my calculator so that I can be, okay. So now 2 minus 0.37, you have 1.63. Okay, 1.63 is left. So 1.63, part of it will go to pipe BD and part will go to pipe BC. Okay, so arbitrarily, it was selected that, okay, 0.5 should go here and the remaining, because when you take away 0.35, you have 1.63. Okay, so we just assume that, okay, 0.5 of 1.63 should go to pipe BC. So 1.63 minus 0.5 is, oh, sorry, 2 minus 0.35. I use 0.37. 2 minus 0.35 is 1.65, not 63. Okay, so when 0.5 is deducted from the balance, you have 1.15. Okay, so the remaining must go here. So if you analyze this junction B, node B, total inflow is equal to total outflow. Total inflow is what? 2. Total outflow, you now sum 0.35 plus 1.15 plus 0.5. Okay? Now, what about, someone may ask, what about in the beginning here? Can I assume instead of 2 here, I just assume 1? And here instead of 2.37, I assume 3.37. Yes, as long as when you add them up, because 1 plus 3.37 is equal to 4.37. So total inflow is equal to total outflow. Okay, so it's not necessary that you must assume the same value, because this is arbitrary. The assumption of the flow rates in the pipes is just arbitrary. It is only guided by the fact that the total inflow has to be equal to the total outflow. That is the most important thing. And that is why when this 2 cubic feet per second comes to joint B, this is the only inflow. All others are outflow. BC is outflow, BD is outflow, and then the nodal demand, which is also an outflow. So when you add these three up, this plus this should give you the total inflow, which is 2. Okay, now here we have 0.5 coming to junction C. Here we have 2.37 coming to junction C. So the total inflow to junction C now is what? 2.37 plus 0.5, which is 2.87. Out of 2.87, you have an outflow already of 0.49. This 0.49 is already provided from the problem. Okay, you didn't assign the nodal extractions. They are to be provided from the problem at the beginning. Okay, so here we have the total 2.87 coming to this junction from pipe A, C, and B, C. Okay, so out of this, we remove 0.49. So the remaining balance is 2.38. So the only way it will flow is through pipe CE. Okay, but when you add 2.38 plus 0.49, it will give you the total inflow, which is what? 2.37, which is the sum of 0.5 and 2.37. Now 2.83 is moving into CE, which is serving as the inflow into junction E. Okay, in this case 1.15 is moving into BD. Okay, when it comes here, out of 1.15, the nodal extraction is 0.42. So we have to say now 1.15 minus 0.42, which is 0.73. So 0.73 must flow here in the other pipe, so that when you add 0.42 plus 0.73, it will give you the inflow, which is 1.17. So you can see at every node, the continuity equation is satisfied. The sum of the inflow is equal to the sum of the outflow. Now, coming to junction E, 0.73 is coming from pipe DE and 2.38 is coming from pipe CE. When you add them up, plus 2.38, it will give you 3.11, which is exactly balancing the outflow here. Okay? So this is very important. You have to understand how to assign this. You have to how to assume the flow rates. Like I said at the beginning, here 2 and 2.37, it doesn't mean you must have it this way. You can change it. But the most important thing, the guiding principle is that the inflow must be equal to the outflow. Simple. And when you look at node A, B, C, D, and E, at all the joints, inflow is equal to outflow. Let's analyze joint D. What is the inflow into the joint? 1.15. What is the outflow? 0.42 and 0.37. So 0.42 plus 0.373 gives 1.15. And that is the same for each of the knots, okay? And here we are assuming clockwise to be positive, okay? Meaning when we come to the analysis, this is clockwise, this is positive flow, but this is negative because it is against the direction of the clockwise. It is counterclockwise. This is also counterclockwise. This is clockwise. So we'll assign clockwise flows to be positive and counterclockwise to be negative. Okay. Now let's move to the next point. You see here we computed K. In the first trial, the flow in each pipe is assumed as indicated in the figure which I have just shown, and the corrections are computed in table 15.6. Okay, how do we compute the correction? We have to compute the head loss for each pipe, and we have to, that's HF, and we have to compute HF over Q, and then apply the formula for the head loss, which is for the correction, which is this one. Okay, we have computed this, and then compute this one, and then we now, N for Hazen Williams, we use 1.85. 1.85. For Darcy Westbach, we use 2. Okay, explain why all this. So let's go to the table and see it. Okay, so this is the table. You see, this is loop 1. Loop 1 is made up of pipes AB, BC, and CA. Okay, AB, BC, and CA. And then this is the K values, which we computed using the Hazen-Williams formula. And these are the assumed flows in the pipes. Okay, this is positive, positive, and CA is negative because it is counterclockwise. And this we compute the head loss HF equal KQA to power of 1.85. Okay, KQA to power of 1.85. We have K, we have QA. So we just multiply them out and raise Q to power of 1.85. And we have to leave the sign. This is negative, so this has to be negative here as well. Okay. So now HF over Q is absolute value. So we remove the negative sign. So that's why here this one is not negative because we use the absolute value in this case. Okay. And here we sum everything up using the algebraic summation. And here we sum everything up as well. And then this is the corrected Q. Okay, which is QA plus delta. So we have to find del for loop 1, applying the formula, which is what? Summation HF over N, which is 1.85, then into HF over Q. Okay, so that's why you can see this is summation HF, and this is summation HF over Q. Okay, so this is the correction for the flow, for the assumed flow rate. So we adjust the flow rate for each pipe by just adding del to the assumed flow rates. For AB, the assumed flow rate is 2. So it will just be 2 plus del 1, which is 2.02, which is this one. Here we also add plus Q, and here for this one, we also corrected the common pipe, okay? We add plus del, which is 0.02, okay? So it becomes minus 0.35. So we will be correcting the flow until this value becomes extremely small. Although as it is also small, but we can make it smaller sometimes, okay? And sometimes it doesn't become so small at the beginning. It may be higher than this value at the beginning. Okay, so that's why it is an iterative procedure. You have to repeat. This is just for loop 1. We do the same thing for loop 2. These are the pipes for loop 2, 4 of them. These are the K values. These are assumed flow rates. You can see BEC is negative because it is counterclockwise. CB is also counterclockwise, the flow rate. Head loss in each one, leaving the sign from the flow rates, okay? And then we find HF over Q, and then we adjust the flow rates, because from here we can find the correction del 2 for the second loop, okay? For the second loop. And don't forget, for the second loop, and don't forget in the formula here that is minus. Yeah, it just didn't show here, okay, but there is minus here, okay? There is minus sign. So we find also del 2 for the second loop, which is 0. So what is the corrected flow rate? Because it is 0, so they are maintained, except they are all maintained. Here we have the common one, which is AC. No, the common one BC. Okay, BC. So which is CB here? Okay, CB. So CB here, we used the original one here. Okay, and then when we correct for CB, because it has to be the same here. I mean, for CB, the correction of flow for CB, it has to be the Asympt flow for CB plus del 1 plus del 2. Okay, del 2 is 0, but del 1 is not 0. Okay, so the same flow here. Okay, in some cases, you know, in some of the problems, when using CB here, instead of using the initially assumed value, we use the corrected value. Instead of using 0.5, we use 0.52, which is the corrected value according to loop 1. Okay, but in this text, they are correcting it at the end of loop 1, at the end of loop 2. Okay, when you have taken care of all, so you now add the 2 correction to the flows on pipe. Yeah, and this is exactly adjusted, you know, for QBC. You can see del 1, and this is del 2. Okay. Now you have to continue, but of course you can see that these values are already small, but it can be smaller. So you repeat again. To repeat now, these are the new flow rates in the pipes, and these are the new for loop 1. For loop 2, these are the new flow rates, which we now go to the second iteration. This is iteration 1, the first iteration. Okay, we may choose to stop here because you can see del 1 is 0.02, del 2 is even 0, but it may be smaller, okay, than this. So we now repeat again. So here, if you look very well, our K values will remain the same, okay, because it's not a function of the flow rate. It is not a function of the flow rate. So we repeat our K values from iteration 1. Then our Q values will change to the corrected values from iteration 1. All this will reflect the corrected values from iteration 1. Okay? All this is like corrected here, but then in this case, although we corrected for CB, but it was not implemented here. It is still using the correction factor for loop 2. Okay, but in other texts, okay, we have to use the corrected value, which is this one, 0.52 here as well. But in this case, it is maintaining it and correcting it only for loop 2, which is whose correction factor is 0. Now we have to compute HF again because it is a function of Q. So we compute it again, and this one again, and then compute again del 1 and del 2. You can see del 1 here is 0, del 2 is also 0. So it means the assumed value are correct. Okay, no need to adjust them any further. Okay, no need to adjust them any further. And in that case, this is the final flow rate. This is the final corrected flow rates. Okay, for the flows in the pipes. So now these are the flow rates that is in each pipe. What about the pressure head? Okay, What about the pressure head? We were given the pressure head at one junction, isn't it? Final flows and pressure head. These are the final flows. Okay, of course, without any minus, because the minus is just showing the direction. Okay, the minus is just showing the direction of flow. Okay, because discharge is not even a vector quantity. So we have the flow rates in each pipes based on the second iteration. Okay, and the final head loss in each pipe based on the second iteration also. Is the final head loss for each pipe. Okay, you can see here which one has the highest head loss. AC. AC has the highest head loss. Why does AC has the highest? AC has the highest head loss. Okay, because probably if you look at the corrected flows, okay, let's analyze it. AC has the highest head loss. Probably part of the explanation is that it has the highest flow rate. Okay, and by having the highest flow rate, K, the head loss is a function of the flow rate in the pipe. Okay, it's a function of the flow rate in the pipe. But there are other factors, which is K now, which is taking care of the length and the diameter. Okay, the length and the diameter. If you look at the length is 1,500 when compared to CE, okay, and the diameter is 12 inch. In fact, all of the, you have 12 inch, 12, 8 inch, 8 inch, okay, most of them 12 inches, okay. So you can explain why it is having the highest flow head loss by looking at the flow rate as well as its dimension. Look at CE also, okay, though DE has low flow rate, but it has high uh, head loss. You can explain that by looking at the length and the diameter of DE, okay? Because the head loss increases when the length increases, and the head loss decreases when the head loss increases when the diameter decreases, okay? For low diameters, you have the head loss to be higher, okay? So if you look at DE, its diameter is 8 inch, while most of the remaining are having 12. Okay, so that is why part of the reason that it is having higher head loss. Okay, although the flow rate is low, but its diameter is smaller. Okay, it has a smaller diameter, and based on the head loss formula, the diameter, you raise it to a given power of 4.87. So the smaller the diameter, the higher the head loss. Okay, the higher the head loss. Now, let's move to the node and calculate the pressure head now. The pressure head for each node. Okay, we were given the pressure head at one point, and this is usually the case. We'll be given the pressure head at one point, and this pressure head will be reducing as the flow is progressing for the subsequent points, because this is the inflow. You can see the inflow is here. Okay, this is the initial inflow into the system. Okay, so the pressure head is given at this point to be 100 feet. Okay, meaning the pressure head is the sum of the okay. No, this is not the piezometric head. So it's simply the pressure head. So meaning if you put a piezometer here, it means water will rise to a height of 100 feet. And 100 feet is 30 meter. Okay, and 30 meter in a story building, it will be multi-story building. it will be probably about, let's say, 9-story, or let's say 8-story building, 8 floors. And that is really a very high story building, isn't it? Let's say 8 floors. Okay, so that is the pressure head at the entrance. What about the pressure head in this node, in that? Because as the water is flowing through the pipes, it is losing the head. There is head loss due to friction. As such, the pressure head is dropping, and the pressure head will be dropping as a result of the pressure, as the head loss in the pipes. Okay, so all we are going to do is to be subtracting the head loss due to friction and be calculating the remaining pressure head. Let's say at this point is 100 feet. What is the pressure head at node B? As it, it will flow from A to B. So here we have to look at the head loss from A to B. Okay, the head loss from A to B. And then that head loss will drop the pressure head. Okay, the head loss will drop the pressure head up to point B. So to find the pressure head at point B, it is now going to be 100 minus the head loss from A to B. Remember, in the pipe network analysis, we found the head loss from A to B. So we just substitute it here to get the pressure head. Okay, and from A to B, the head loss is 2.46. Okay, is 2.46. So this 100 minus 2.46. So the pressure head at point B is now 97.54. Okay, this is in feet. So you can see the pressure head has dropped because of the fact that it has traveled from this point to that point. Okay, and what about point C? What about point C? You can move from A to C also. You have the head loss AC, which we found, isn't it? We do the same thing. We say 100 minus head loss from A to C. And the head loss from A to C, based on the calculation, is what? 4.91. Okay? And then when you subtract, you have 95.09 as the pressure head in C. You can see the pressure head has dropped. Now, you now move to, let's say, point D. Okay, at B here, the pressure head is 97.54. Okay, when the water moves from B to D, this pressure head will drop because of the head loss due to in the pipe BD. Okay, so now what is now the pressure head here? At this point, it is going to be the pressure head at B. Okay, the pressure head at B minus the head loss in BD. Okay, so which is now going to be simply 97.54 minus the head loss in pipe BD, based on the calculation that we have. Pipe BD has head loss of 2.01. Okay, so this is simply 95.53. So this is now the pressure head. You can see it started 100 here, dropped to 97 here, 0.54, and dropped further to 95.53 here. Okay, and then the last one, which is E. Okay, the last one, which is now E. E here, we can have it from 2 points. Okay, you can see at C here, the pressure head we found is equal to the 100 minus the head loss in AC, which gives us 95.09. So we now remove the head loss in pipe CE. Okay, and the head loss in pipe CE is 3.68. Okay, so that gave us 91.41. Okay, what is the pressure head at point C? Okay, what is the pressure head at point C? Okay, DE 4.06. We can also get the pressure head here by looking at the pressure head at point D. Okay, at point D is 95.3. When it moves here, you remove minus the head loss in pipe DE. Okay, and when you do this, you will arrive at almost the same value here. Okay, so the pressure head at E can be found using the pressure head at D or at C. Okay, so and this is how this table is arrived at. You can see it here. Okay, so this is the pressure head. So you can see that point C has the least pressure head. Point E, I mean, okay, because the water must have traveled all the way either through this route, this one, okay, or this, and that. Okay, so it has the lowest pressure head. So meaning the lowest pressure head here is about 91.41. You know, the total inflow, the total pressure, the starting pressure head is 100 feet, but it has dropped to 91.41. Okay, and that is why sometimes if the pressure head drop is so high, because when water is flowing through long pipeline, you have pressure head is dropping. So that's why you need booster pumps to increase the pressure of the flowing fluid so that it will arrive at the destination at the the residual areas at the required pressure head. Okay, you can imagine that the pressure head drops, let's say, to around, let's say, 10. That may be very low. We are going to see in the design that the pressure head has to be certain minimum in the pipeline. Okay, the pressure head has to be certain minimum in the pipeline. Okay, so do you understand? Because we'll reserve the design of a water distribution system for the next class, but we will still be referring to all that we did here. You see, what we did in the pipe network analysis, generally, we found the flow rates in the pipe. Okay, all we have in from the problem is the total inflow into the distribution network. And based on our calculation, we distributed the flow rate. We assumed the flow rates and adjusted them until we found the final discharge in each pipe. And then this is the final head loss in each pipe. Based on the head loss in each pipe, we can now know the pressure head for each node, which is very important, because at the end, that pressure head is what will be able to, let's say, lift the water can be now conveyed to the highest rise building in the area and all that. Okay, so this is very important, the pressure head and the flow rate in the pipe. Okay, as we are going to see, they have to be certain minimum. Okay, so the analysis, pipe network analysis, is very important. It's the preliminary stage for any water distribution system design. The first thing you do is the pipe network analysis. And as you can see, it is somehow cumbersome. Somehow, it takes time, iteration. This one, iteration 1 and 2, we stop. Sometimes you may do probably 4 iterations, 5 iterations before the adjusted flow rate, the del becomes very small that you can stop. You may have to go many iterations. Okay, and of course you can use Excel to be changing the values. It will be simpler when you write the formulas inside the Excel sheets and be making your calculations. Or if you have any programming knowledge, you can simply program it. Like I said, during my what we have at the time, our undergraduate research project, I developed a Fortran program whereby you can just enter, everything, the Asympt flows and all that, and that it will be taking you through all the iterations, giving you the corrected values until, the flow rate correction value becomes small and you stop. Okay. So any question on the Hydrocross method of the pipe network analysis? You will still have to take your time, and try to do it. Every value, try to use your calculator and make sure you can arrive exactly at each of these values, okay? And then at any point in time, if you have any question, you can send me a WhatsApp, and because it's very important, pipe network analysis. And like I said, the next stage is the water distribution system design, and we'll be referring to the analysis part of the pipe network. Okay, we'll be referring to the analysis part. Now I have full house. So Amjad is back. Yeah, structure same as circuit. Yes, same as circuit diagram, for electricity. You are right, and for electricity, there also they use what is called the Kirchhoff's law. Kirchhoff's law, in which you have the inflow at the junction equals the outflow. Yeah, the analysis is similar to a circuit analysis of a circuit diagram. So if you don't have any further questions, so we see um, uh, uh, we will meet in the lab, okay, where we will discuss about the assessment criteria and then see what we can arrive at, okay. And then of course, you are going to work on your term project, okay, which you are presenting next week. Yeah, both groups, yes, both groups at 2, both groups at 2 in the lab. Okay, so take your time to look at this Hydrocross method, okay, analyze it, okay, and see you.